Okay, so today we're going to do the first main theorem of the course. Actually, it's really two theorems, but they're very closely related to each other. So it's kind of one major body of results. But more important than the result itself is the technique that we're going to introduce that's going to allow us to prove the result. And this is a very important technique in logic called quantifier elimination. It's only applicable in certain circumstances, but when it is applicable, as it will be today, it gives very powerful results. And this topic, quantifier elimination, is going to be the topic for the next 2 weeks. So next week, we're going to see a more substantial application of this technique than the one we're going to see today. Sorry, let me just check. Yeah, everything's working okay on the computer. Right, so actually, I'm just going to begin by stating the main result we're going to prove, and then it's going to take us the whole lecture to prove it. So it is a substantial result. In order to state the result, we need the notion of what it means for a theory to be decidable, which I've already talked about in both of the two introductory lectures, lecture 1 and lecture 2, but now we're actually going to prove a theorem involving it. So let's do ourselves the service of giving ourselves a definition. So we say a theory P. Remember, a theory is a set of logical sentences closed under logical entailment, is decidable if, and the informal definition, which is going to be good enough for us in this course, if we can construct, or if there exists an algorithm so a precise set of instructions that allows us to compute. So informally, you can think of that also as a computer program. The precise definition of algorithm involves, well, any one of a number of models of computation, which are not the topic of this course. So this is not important for this course, which is why it's in blue and why it's in brackets. But just to say, one can make this notion of algorithm precise by the notion of Turing machine. But if theory is decidable anyway, we can just think of the notion of algorithm imprecisely. If there exists an algorithm that takes sentences as input, well, takes a sentence as input, but takes sentences as input, and eventually, then you give it its input sentence, then it goes off and computes for a while. And after computing, it's important that it eventually responds with an output. And this output tells us, let's, instead of say sentences, let's say it takes a sentence A, in order to have a notation for the sentence, and the output will tell us if the sentence belongs to the theory. So it's going to output true if, well, if A is a logical consequence of the theory, or equivalently, if A is a member of the set of sentences T, because remember that our definition of theory is a set of sentences closed under logical consequence, and it's going to respond false. Maybe it's better to say, it obviously doesn't matter. Can anyone see the, yeah, here they are. Obviously doesn't matter what the computer program responds, but let's just say yes and no instead. The reason for that is I don't want to confuse the answer of the machine with the logical truth of the sentence. So we're not looking for truth, we're looking for validity. So if it's so we're looking if it's a logical consequence of the theory, and no if it's not a logical consequence of the theory. So A is not a logical consequence of the theory. So equivalently, if A does not belong, the sentence A does not belong to T. And our main theorem, as I said, there are actually going to be two theorems, but this is the one we can state immediately. The theorem A is this, our main theorem then is that theory of logical validity, namely our theory is the theory of logically valid sentences, but over a special signature, in fact a very simple signature, the empty signature, over the empty signature is decidable. So if you have a sentence, a logical sentence, that does not involve any predicate symbols from a signature or any function symbols from a signature, then the validity of that sentence is decidable. So in a sense, it's not so surprising, because if you have an empty signature, you've got no vocabulary. And if you've got no vocabulary, you can't say very much. So if you can't say very much, it's not that surprising that we can find an algorithm to test the validity of a sentence. But nonetheless, you will see that there's more to this than meets the eye. It's not actually a trivial result. It involves quite a bit of work to get it. And that work involves also a little bit of mildly interesting combinatorics in it. Okay, so just to show that we can say something over the empty signature, let's have a look at some examples. You may just think if you don't have any vocabulary, you can't say anything at all. Well, babies manage to communicate with their parents without any vocabulary. So not sure that's relevant to logic, but just occurred to me. So in logic, what can we say without any vocabulary? Stick with black. So let's have a look at some example sentences over the empty signature. And actually, you've considered some of these examples in exercise classes. So example sentences over the empty signature. So let's call it sentence A1. We're going to define sentence A1 to be there exists an X, there exists a Y, or as you know, we tend to abbreviate that, we just write there exists X and Y, not X, such that X is not equal to Y. So there exists an X, there exists a Y, such that X is not equal to Y. But this sentence is not valid because it's not true in the structure that has exactly one element. And in fact, it states the property that a structure has two or more elements. So this is true. So A1 is true in structures whose cardinality is greater than or equal to 2. So it is not valid because there exists a structure whose cardinality, there exist structures whose cardinality is 1. It's not valid. We can negate this sentence. Let's call it A2. So not that, or we can define the same negation more positively. So for all x, for all y, so again, we just write for all x, comma y, x equals y. And A2 is true in structures, obviously it's negated, in structures whose cardinality is strictly less than 2. In other words, whose cardinality is less than or equal to 1, so structures that have at most one element. Now, it's not something I emphasized in the first lecture on structures, but in logic, it is traditional to make the assumption that the underlying set of the structure is non-empty. It doesn't really matter whether you make that or not, but it's traditional to do it, and so we are going to do that. And if we make the assumption that the underlying set of the structure is non-empty, this is true in structures whose cardinal exactly in those structures whose cardinality equals 1, because we don't have the empty structure. So again, it's not valid. Maybe just a comment on this. Why do we assume structures are non-empty? Well, it makes life a little bit simpler when we come to give proof systems for the logic, which is something we're going to do in 2 lectures' time. So it makes the principles for reasoning with quantifiers slightly easier if you know that you're dealing with a non-empty structure. And of course, since any interesting mathematical situation will involve a non-empty set, then you're not really losing anything by this assumption. That's the reasoning that one normally uses. Okay, so those are 2 non-valid sentences, but they express interesting properties of structures. And of course, A2 is the negation of A1. If we consider the disjunction, this is valid. So our algorithm in the end, if we pop, we're going to come up with an algorithm. And for the purposes of doing so, we can consider the algorithm to be informal. We're going to just give some precise steps that will allow us to, that would allow us, if we were patient enough, to write a computer program that could input a sentence to and it would come up with yes or no as appropriate. If we gave our computer program, if we programmed it correctly, if we gave it this input, it would say no because it's not valid. If we gave it this input, it would say no because it's not valid. If we gave it this input, it would say yes because it is valid. Okay. So this sentence here is an example of an important family of sentences that you've also considered in the exercise class, I think. So important family of sentences. So for any n greater than or equal to 1, consider the sentence, there exists x1 up to xn. So these are n existential quantifiers in sequence. And what we want to say is there exists x1 to xn, so there exists n elements in the structure, and they're all different from each other. So I want to say no 2 of these are the same. So we can do that by, we do a conjunction from I of counting up from I is 1 to n minus 1. And we're going to say that xi is different from, we don't want to say xi is different from itself, that can never be true. So we want to make sure we go over the other xn. So then we count up from j, we count up from I plus 1 to n. And we say that xi is different from xj. So this large conjunction. And notice in the case that n equals 1, so if n equals 1, the sentence is, well, exists x1. So just to show you what the sort of simple base cases, in the case n equals 1, then we've got a conjunction over n minus 1 things, that's a conjunction over 0 things, and then we don't have any index here, so this is just the empty conjunction, and the empty conjunction is true. So if n equals 1, the sentence is this, which is just simply the valid, which is just a valid sentence. So this is, remember, the truth constant, not a t here. And you can see, I hope, immediately, that this sentence expresses the property that the cardinality is true in a structure whose cardinality is greater than or equal to n. So we shall call this sentence cardinality greater than or equal to little subscript there. So I'm simply using this as a notation for this sentence. And so this expresses cardinality is greater than or equal to n. Good morning. And its negation, we negate that sentence, expresses, of course, the cardinality. It's not true that the cardinality is greater than or equal to n. In other words, cardinality is strictly less than n. And so I won't write it down, but for example, we can say we've got a sentence that says the cardinality of the structure equals n, namely cardinality greater than or equal to n, and not cardinality greater than or equal to n plus 1. So that would express that the cardinality exactly equals n. So these are examples of slightly non-trivial things we can say using sentences with the empty vocabulary. We'll see some more examples of sort of more complicated things a little bit later. Right, let me clear the board. So the way we're going to prove our main theorem is using this technique of quantifier elimination. So let me just tell you what that means, and then we'll take quite a bit of time to see how it applies, and how it applies to this theory of logical validity over the anti-signature. And actually, it doesn't directly apply to this. We need to change the situation a little bit to get quantifier elimination to work. We're going to need to do a bit of work to prepare ourselves to be able to use quantifier elimination. But let's see what we're heading for first. So I already have the title, quantifier elimination. So let's keep that. Now, quantifier elimination is, on the one hand, a very simple concept because it literally implements what you think it should, given that it says, it suggests that we're going to eliminate quantifiers, and that's exactly what we're going to do. On the other hand, there is a subtle point associated with it that is very, very important to appreciate. So I shall highlight that in a moment when I write it down. So in order to define quantifier elimination from a theory, which is what we are really interested in, I'm going to work with what it means to say we can eliminate quantifiers from an individual formula. So I'm going to use the following definition. We say that, it's okay. So we say that quantifiers are eliminable from a formula A relative to a theory T and let me underline all of that because in a sense, every part of this phrase is important. Although one would be more concise quite often. So what this means is it means we can find, so this is a first order formula. So it's built up. I'm now not talking about just the empty signature. I'm talking about any vocabulary here, so any signature and any first order formula over the signature. So we're built up from the atomic formulas using the connectives and the quantifiers. And quantifiers, we say the quantifiers are eliminable if we can find an equivalent formula, equivalent in the theory, that contains no quantifiers. Okay, so an equivalent quantifier-free formula. So if there exists a quantifier-free formula, I'll write superscript QF, such that the quantifier-free formula is equivalent to A in the theory T. So such that in the theory T, we have the we have the by implication, the if and only if, saying that the quantifier-free formula is actually, I prefer to, it obviously doesn't make a difference, but for aesthetic reasons, I prefer this on the left-hand side. The quantifier-free formula is equivalent to A. Okay, so this is kind of correct what I've written, but I've ignored the subtle point. And let me tell you what the subtle point is. In order for quantifiers to be eliminable from a formula A, notice we're talking about a formula, not a sentence here. So the formula might contain free variables. And what's important is we sort of observe which free variables we have. I'm going to use this notation here. This means, when I write this, it means the formula A has its set of free variables are contained in the set x1 through to xn. So any free variable in A is one of x1 through to xn. We could write it like this and include some variables here that do not actually occur free in A. We're allowed to say that, but the point is, if we write this, every free variable in A must occur in x1 through to xn. So let me write that down. This is notation. A x1 to xn means, so in the notes I have this this is the set of free variables of the formula A. It means that the set of free variables of the formula A is a subset of x1 through to xn. When we write this, we assume we only write this using a tuple, a vector of n variables in which every variable is distinct. And the point is, the important subtle point is to say that quantifiers are eliminable for a formula. It's crucially important that the quantifier-free formula does not introduce new free variables into it beyond those that we've already said it can have. So we require that there exists a quantifier-free variable formula that has no more free variables than the ones we've already identified. And then what do we want for the equivalence? Well, we want this if and only if to hold universally quantified over those free variables. So for all x1 through to xn.
There was a question. If
yes,
the three variables of A are just a subset, then the quantifier-free formula can have more than
yes, that's true.
three variables of A, but they still have to be in the X.
Yeah. So it's true if we give a formula A and we say we're giving this formula A and identifying the formulas x1 through to x1 million as our free variables, when actually A only had one free variable, then our quantifier-free formula would be allowed to occur to contain variables x1 through to x a million. But we could also, but if we're going to have quantifier-free elimination in general, it would have to work also if we only identified variable x1 here. In which case, so there will still have to be a quantifier-free formula that does not introduce any more free variables. So the point is, we ask for quantifier-free elimination to hold for a formula with respect to a declared set of free variables. And the quantifier-free formula must not introduce any more free variables beyond the declared set. But we're going to ask for quantifier elimination to hold for all formulas and for all and for any reason, for any legitimate set of identified free variables. And so if that holds, then there has to be a quantifier-free formula that does not introduce any free variables. Let me introduce some more notation here. So this is the way we say that a quantifier-free formula, well, this is the way we say that two formulas with the same set of free variables are equivalent over the theory T. So notation, given two formulas, A, B, same sets of free variables, well, where we're identifying a common set of free variables. We write A is equivalent to B over the theory T. Then we have the notion of logical equivalence, means the by implication is valid, the if and only if between the formulas is valid. We say it's equivalent over the theory T to mean that by implication is true, is valid, is a consequence of the theory T. And that by implication holds for all instantiations of the free variables you can identify x1 through to xn. Okay. And now, finally, more important definition. Say, theory T enjoys quantifier elimination if quantifiers are eliminable from every formula with a legitimate set of identified free variables. So that set must contain all the free variables in the formula. So if quantifiers are eliminable from every formula A together with every formula A together with a legitimate set of identified free variables that contain all the free variables in A. So the other slightly subtle point here, a theory is a set of sentences. So there are no free variables in the formulas occurring in the theory itself. But for the theory to enjoy quantifier elimination, we're not just stating a property about sentences, we're stating a property about formulas that contain free variables. And it's fundamentally important, it's crucial to everything that we're going to do with quantifier elimination, that we can eliminate quantifiers not just from sentences. So sentences are a particular case when we don't identify any free variables here. It's crucial for the theory to enjoy quantifier elimination that we can eliminate quantifiers from formulas that do contain free variables. But notice that eliminating from this definition, if we have a sentence and we want to eliminate quantifiers from a sentence, well, then we look at the sentence together with the empty tuple of free variables. And this definition requires that the quantifier-free formula, it's over the same, it contains its free variables are also contained in the same set. So the quantifier-free formula will be forced to be a sentence too. So as a consequence of this, this implies that every sentence is equivalent to a quantifier-free sentence. But it's stronger than that because it's saying every formula is equivalent to a quantifier-free formula in the same set of free variables. Okay, so as I say, the issue to do with variables is the subtle point here. Apart from that, it basically says what you expect. You can eliminate, you can remove quantifiers from formulas. Are there any questions on that while I look to see what's coming next? Okay, so maybe we can do one result, which is going to be useful. So a lemma, if you like, which is something we're going to use to help us prove that theories have quantifier elimination, and then we'll have the break. So we could state it as a lemma, and in my notes I've called it a proposition, so I think I'll keep the same terminology. What we're going to do is provide the necessary and sufficient condition for a theory to have quantifier elimination. The interesting point is that it's a sufficient condition. It means it's enough, in order to show that a theory has quantifier elimination, it's enough to show it for formulas, not for sentences. It's enough to eliminate quantifiers from formulas that are in a very simple form. And then once one's observed this, then the main difficulty in actually showing that you can apply quantifier elimination in specific cases is then dealing with the mathematical nature of eliminating quantifiers from the particular formula form in question. So let me just, it's hard to say at an abstract level without having something concrete to look at. So the proposition is this, so this is a really useful proposition. A theory T enjoys quantifier elimination I just write quantifier elim dot. If and only if, for the purpose of this dot is to say I'm eliminating the word, I'm abbreviating the word elimination, it's not an end of sentence. Elimination if and only if quantifiers are eliminable, bit of a tongue twister. Quantifiers are eliminable from formulas of the form, and actually one could consider very simple formulas. The formulas of the form, so we only need to consider formulas with one existential quantifier, followed by a conjunction of literals. And very, very simple formulas. This part's quantifier free. On the inside, it's a conjunction of literals. Remember from last week, a literal is a formula that is either an atomic formula or the negation of an atomic formula. So where each Li is a literal atomic formula or the negation of an atomic formula containing the variable x. Okay, so it's necessary and sufficient to prove quantifier elimination, to prove the eliminability of quantifiers from formulas of this very specific form. So it's absolutely obvious that if quantifiers are eliminable, then they're eliminable from formulas of this specific form, because if they're eliminable from all formulas. So the left to right implication is obvious. So for the right to left implication, which is if we can eliminate quantifiers from formulas of this form, then we can eliminate quantifiers in general. So for the right to left implication, suppose we can eliminate quantifiers from all formulas of the above form. So let me give a name to this form. I'll just call it asterisk, star if you like, star. So we suppose we can eliminate quantifiers from formulas of this form. We want to show we can eliminate quantifiers from all formulas. So we're going to do this in a number of stages. In fact, one way to do it is to give a sort of case-by-case, like inductive little algorithm that will do this, but I'm going to do it at a bit more high level, just to think it's easier to follow than being sort of splitting things into lots of precise cases. So step one, we show we can eliminate, and this is the main step, eliminate quantifiers from all formulas of the form exists XA, where A is quantifier free. So again, we've just got one existential quantifier to eliminate, but now this can be any propositional combination of literals rather than just a simple conjunction of literals all containing X. Well, we have, because A is quantifier free, we have by last week, A is equivalent logically to a formula in disjunctive normal form. So we have A is equivalent to so in that case, exists XA is equivalent to exists X C1 or C, do I use here M in my notes, CM, where each C, where each, so remember, disjunctive normal form says the quantifier free formula is equivalent to a disjunction of conjunctions of literals. So each CI is a conjunction of literals. Okay, so A is equivalent to this disjunction, so exists XA is equivalent to exists X, this disjunction. But then we can use the distributivity of existential quantification over disjunctions, so that A is equivalent to there exists X C1, or there exists X CM. And now each CI here is a conjunction of literals. So we can write CI is equivalent to, I mean, it's literally can be written as, it's a conjunction of literals, so it's going to be some L1 conjunction of L1 up to LK, where let's split the literals into two parts, those that contain the variable X and those that do not contain the variable X. So we'll also say L1, L prime 1 up to the literals that don't contain the variable X. That's called, I suppose there are K prime of those. So here, I'm assuming that these contain X and do not contain X. If we look at any of these exist X CI, so we then have exist X CI. It's equivalent to logically. Well, remember if we've got exist over a conjunction, it doesn't distribute, but if the variable that you're quantifying over doesn't occur in one of the conjuncts, you can pull that conjunct out. So we can pull all these L primes out. So this is equivalent to exist X L1 conjunct to LK and L1 prime and LK prime, L prime K prime. And this is exactly the form star that we started with. So by our assumption, this is equivalent to a quantifier-free formula. So by assumption, this is equivalent to, by now, for the first time, we're using equivalent in the formula in the theory T rather than just logically equivalent. This is equivalent to some B, let's say BI, and L1 prime and L prime K prime, where this is quantifier free. And we could just say, let's call this whole thing is a quantifier free formula. Let's call this CI. No, I've already got C's, and we've got D's. Have I got B's? No. Let's call this. I'm departing from my notes here, but I don't really care. So let's call this D sub I. And we see now that exist XA is equivalent to, so formula we started with, exist XA, is now equivalent in T to the disjunction of D1 up to D. How many? So we're coming from here, we had m different such existential formulas over a conjunction of literals. We've shown that each of these is equivalent to a quantifier-free formula. So we've now got m different quantifier-free formulas, D1 through to Dm. So we've shown that the formula we wanted is equivalent to a quantifier-free formula. Right-hand side. The right-hand side, r.h.s, is quantifier, quant.free. Okay, so we've dealt with step one. We've eliminated quantifiers from all formulas of the form exist XA. So step two is an arbitrary formula. Step two, eliminating quantifiers from an arbitrary formula. From an arbitrary formula. But this is now easy because last week we saw that, and it's anyway a very easy observation, we saw that you don't need to have the universal quantifier. You can define it in terms of the existential quantifier. So given an arbitrary formula A, rewrite it using only the existential quantifier. You rewrite it using only existential quantifiers. And now I'm just going to explain what to do without writing it down. So this is where we could make it very precise, and it wouldn't take a lot of work to make it precise, but it's easy to understand the high level idea here, which is we work from the inside of the formula outwards. And you go to an innermost existential quantifier. So one that inside the existential quantifier, you don't have any more existential quantifiers. And step one tells us how to eliminate that existential quantifier. So you eliminate that existential quantifier and replace it with the equivalent quantifier-free formula. You then carry on doing that. So for each existential quantifier, each time you still have an existential quantifier, you take an innermost one. So there are no existential quantifiers inside it. Use step one to replace that existential quantification with a quantifier-free formula, and then you've eliminated one more existential quantifier. You do that for all the existential quantifiers in the formula, and at the end of the process, you're done. So let's just write simply eliminate existential quantifiers, eliminate existential quantifiers, existential quants. I'll write one by one from the inside out. And we're done. And so it's 3 minutes past. So I remember people like to have 15-minute breaks. So we shall start again at 18 minutes past. Okay, I'll pause the video. Right, so we proved this result, this proposition that says if we want to show that a theory enjoys quantifier elimination, it's enough if we find an explicit way to eliminate the quantifiers from formulas in a very simple form, this existential quantification over a conjunction of literals, each one of which contains the variable x. So just a couple of remarks about what we did in the proof. So everything we did in the proof was algorithmic. We start with, we want to eliminate quantifiers from a formula A. We write that, if we take the whole proof, as I explained it, we take the formula A, we rewrite it by replacing all the universal quantifiers by existential quantifiers, so not exists not. We then go inside the formula, starting from the inside existential quantifiers, reach an existential quantifier where we've got existential quantifier followed by a quantifier-free formula. We convert that quantifier-free formula to disjunctive normal form. We then do the steps that I've eliminated from the board here to replace that whole existential quantifier over the quantifier-free formula with the whole thing with a replacement quantifier-free formula, and we repeat that process for every existential quantifier from the inside out. So, as long as we have an algorithm for doing this step, we get an algorithm that, given an input formula, produces us a quantifier-free equivalent formula. So if we have an algorithm, computer program, if you like, that eliminates quantifiers from formulas of the form star, then we get an algorithm that eliminates quantifiers from arbitrary formulas. We give it an input formula, and it gives us as output a quantifier-free equivalent formula. at the same time, we might tell it what free variables to work with from arbitrary formulas. Is this, however, an efficient algorithm? Why not? Yes. So as I mentioned last week, converting to disjunctive normal form is inefficient. And every time we eliminate a quantifier here, we convert to disjunctive normal form. Of course, you might start off with the formula in a nice form, in which case you might not have to convert to disjunctive normal form at the beginning, but still, as you go through the algorithm, it's not going to maintain that nice form. And in particular, it turns out if you have alternations of quantifiers exists for all, then these algorithms get very, very complex because the for alls put lots of negations in. So it is not an efficient, it is not, but we're not going to worry about efficiency. It is not an efficient algorithm. Won't write it down, but because it involves conversion to disjunctive normal form. Okay, so what I want to do, as you will probably have guessed in this lecture, is I want to apply quantifier elimination to the theory of valid formulas over the empty signature. There's a problem in doing this. While I'm clearing the board, I don't know if anyone can guess what the problem is. No? So goal, apply quantifier elimination, so quant elim to the theory of valid sentences over empty signature. That's right, empty signature. Anyone guess what the problem is? Problem is this theory does not enjoy quantifier elimination. So not enjoy quantifier elimination. We've already seen an example. For example, the sentence for all, that doesn't matter which one we do, but exists x, exists to y, x is not equal to y. This is not equivalent to a quantifier-free sentence. So this is not equivalent to a quantifier-free sentence. Why not? Well, I mean, I'm assuming here we've got a signature involving true and false. If we don't have that, then we don't have any quantifier-free sentences at all. But if we need to have the propositional truth values true and false. And in which case, all quantifier-free sentences are Boolean combinations of the true and the false constants. They're the only quantifier-free sentences. So the only quantifier-free sentences are Boolean combinations. So by Boolean combinations, I mean combinations using the propositional connectives and or negation. Boolean combinations of true and false. So, e.g., say true and false or true, something like that. the sort of thing you might have as a quantifier-free sentence. And as you can hopefully all see, any such Boolean combination of truth values just evaluates to a truth value very simply. And any such just simply go through truth tables. And any such is equivalent to true or false. But this is not equivalent in the theory of in the theory of valid sentences over the empty signature is not equivalent to true or false, because this is true in some structures, namely those structures that, as we saw, that have at least two elements, and it's false in other structures, namely those structures that have exactly one element. So it's not equivalent to either to true or false. It's not logically equivalent to true or false over this theory, which is the theory of logical equivalence. Okay, so what are we going to do? Well, we're going to extend our theory by adding propositional constants for representing these properties. And that's going to be enough. If we add propositional constants representing these properties, then this will be equivalent to a propositional constant, which is now a quantifier-free sentence. And it turns out that's enough to be able to express any first-order logical property over this signature. And that's the relatively deep result, that last part. So I want to extend, so I now want to give ourselves a signature that involves some logical constants. So I'm going to do this using a general procedure, which I'm going to introduce in general. So this is extending a signature with definable predicates. Extending a signature with definable predicates. So let's consider an example. And the example I'm going to consider, I'm going to go back to an example from the first lecture, the signature for the natural numbers where we have 0 plus 1 and multiplication, addition and multiplication, e.g. signature of 0 plus 1 times, thinking of it as for natural numbers. And we saw in the first lecture that in this signature we can define the strict less than relation, and also the prime, the property of being a prime and things like this. But let's just look again at the strict less than relation. In this signature, we can define the x is less than y, that's equivalent to, that there exists, you might remember, there exists a z such that y equals x plus z plus 1. Then you have two options how you deal with less than. You can either work with the original signature and use less than as a shorthand, an abbreviation for a more complicated formula that you don't want to write down. So in lecture 1, we used x less than y as an abbreviation for a more complex formula, as above. Well, to be more precise, we can say for the more complex formula on the right. But the point is, we didn't change the signature. The alternative is, actually another thing we could do is give ourselves this relation, make it a bona fide predicate symbol in our vocabulary, in which case we then literally have a formula, x is less than y, and we don't need to consider it as an abbreviation. But of course, it will still satisfy the property that it's logically equivalent to this. And sometimes it's useful to extend the signature. For example, if we don't have quantifier elimination, if we don't extend the signature, but if we do extend the signature, we do get quantifier elimination. So that's a useful case which is pertinent to what we're about to do, where it is useful to extend the signature. So an alternative extend signature by adding a new binary predicate, So the new signature in this case would be, so we still have 0 and plus and 1 and times, but we also then have the primitive less than relation and add the defining equivalences x less than y if and only if there exists a z such that y equals x plus z plus 1. And really, we're adding them to the theory, so really we try to add a sentence. So it's for all x and for all y, x is less than y if and only if this. We add these defining equivalences to the theory. The theory we are working with. Okay. And the general process here is very easy. So this is a very simple example. The general process so given theory T and an identified formula from chosen formula A that might have n free variables in it, we can define an n-ary predicate symbol to represent the formula A. If we want to, we might choose to extend the signature with an n-ary, with a new n-ary predicate symbol that defines the formula A. So we can choose to extend the formula, the signature, by adding a new n-ary, n-argument predicate symbol P, P to the signature, and adding the sentences for all x1 through to xn, p x1 of xn holds if and only if A to the theory. Okay, so if we consider whatever theory we're working with in a particular signature, and we add a new axiom to the theory, which is this one, saying the new predicate symbol we're adding to have that in our vocabulary is forced to have the same meaning as the formula A. Notice that, I mean, here I'm writing A, whereas here I wrote A x1 through to xn. They mean the same thing, it's just here I'm saying we have a formula A that contains at most the free variables x1 through to xn. So here, the formula A will contain within it at most the free variables x1 through to xn, and it's always equivalent to this predicate symbol. We're defining its meaning to always be equivalent to n. Okay. So doing that, I can define the theory that we're going to work with now. Ah, I see I didn't change the camera position for the, well, anyway. I don't know if somebody on Zoom, maybe there are a few people on Zoom, maybe they're all asleep. Can somebody shout just so I can hear if... Oh, okay, no microphone on the device. Okay, well, anyway, never mind. Well, let me just show that board so that it's there for the video. While I'm showing that, I might as well clear the other board. Well, we're not doing so badly. This is, I think, the first. Well, we haven't had that many technical hitches over the first 4 weeks. But anyway, it is a bit hard to always remember to take the camera position. Right, so what we're going to do is we're going to work with a theory, which this is my name for the theory. It's not normally given any name at all, but I thought it's useful to have a name. So FCB, I call it finite cardinal bounds. So the signature is, I'm going to add lots of zero-arity predicate symbols. So one for each natural number n greater than or equal to 1. So each c greater than or equal to n is a propositional constant. That's a propositional constant. That's a zero-arity predicate symbol. Together with the equivalences, the axioms, stating that each of these is equivalent to the, so c greater than or equal to n, that atomic propositional constant is, it says the same thing as the sentence card greater than or equal to n. So plus the axioms for each n, we don't need any quantifiers because these have zero arguments. But for each n, we add the axiom that c greater than or equal to n says the same thing. So this is now a quantifier-free formula here because it's just a propositional constant. It says the same thing as the formula card greater than or equal to n. So this is quantifier-free formula. And this is the sentence we considered a sentence defined earlier. The one exists 1 through to exists n, some conjunction of inequality, of not inequalities, but non-equalities. Sentence defined earlier. And so it solves the problem we had before, that as e.g., so before we had the sentence card greater than or equal to 2, exists x, exists y, such that x is not equal to y. There is no quantifier-free formula that's equivalent to that. This is now equivalent to the quantifier-free formula. Well, in fact, the quantifier-free sentence c greater than or equal to 2. Okay, so it doesn't look like we've done very much. I mean, looks like we might have trivialized things, but I think by the end of the proof, you'll hopefully agree with me that it's not completely trivial. That the point is, we're going to show now the theorem. We're going to prove in the rest of the lecture the theorem, and the theorem is, as you may guess, so this is theorem B. The first theorem of the lecture, I don't know if I remember to call it theorem A, but that was theorem A, the one about decidability. So theorem B is, as you may guess, theory FCB, finite cardinal bounds, enjoys quantifier elimination. So it's enough to have constants expressing these cardinality constraints. And the deeper result from that is, no matter how complicated a formula you have, involving whatever combination of logical connectives and quantifiers, it can be reduced to a Boolean combination of these cardinality constraints. And to give you some feeling, so for how complex this is, I'm going to give you a little puzzle to think about. We're going to have the break soon, but come on, camera. Right. So, of course, the proof is going to be that we show how to eliminate quantifiers from formulas in the form star that we had earlier. So the existential quantifiers over conjunctions of literals, all involving the variable that we have in the existential quantifier. So the puzzle for you to think about, if the lecture is going too slowly and you have some background cycles available in the back of your head, then the puzzle is, what is the quantifier-free formula there are many possible, what is a quantifier-free formula equivalent to the formula that exists at x, so it's going to be a conjunction of literals all involving the variable x. And in fact, we can reduce it further to ones of a very specific kind. So it's a conjunction of statements that x is different from k different variables, okay? You need to find a quantifier-free formula that expresses that conjunction. And the quantifier-free formula can involve the variables, in fact, will need to involve the variables y1 through to yk. Okay? And actually, while you're thinking about that, I mean, you probably, just in case you've already started, let me just do a simple case for you. So I'm going to, before giving the proof, I'm going to eliminate quantifiers from two particular formulas to see how it works. So example one is actually going to be an instance of this where k is 2. So we're going to do, well, I'm going to call the variable z, just to confuse you a little bit. And we're going to say z is not equal to x and z is not equal to y. So what's the quantifier free formula in this case? Well, one way in this that this can be true is if the cardinality of the structure is at least 3, because then whatever x and y are, you can always take z to be that at least one other element is going to be left, and you can take z to be that. Okay, so the quantifier free formula part of the truth of that formula is that the cardinality is greater than or equal to 3, which we can express using a propositional constant, c greater than or equal to 3. But that's not the only situation in which this can be true, because the other situation in which this can be true is, well, what happens if x equals y? Well, in that case, this will be true whenever the cardinality is at least 2, because if x equals y, it's then one of those elements, and you can take z to be the other. So there are two possibilities, and the disjunction of them is equivalent to this formula. So either the cardinality is greater than or equal to 3, or x equals y, and the cardinality is greater than or equal to 2. Think about it a little bit. You can see that this formula implies that, and this formula implies that. Okay. So you're going to have to think along similar lines as you go, as k gets larger, the considerations that went into that get more combinatorial. Nice little clue. So maybe we do one more example and then we have the break. So the next example is going to be a sentence, and we can also view this example as at the end we want to prove that the theory of finite cardinal bounds has quantifier elimination, but we also want to get an algorithm for deciding the validity of sentences. We're going to get that from the quantifier elimination procedure. So look, going back to thinking about theorem A at the start, when I said that the theory of valid sentences over the empty signature is decidable, if we start off with a sentence, we also want an algorithm that's going to tell us if the sentence is valid. So let's start off with a sentence and consider how our algorithm is going to work. And our algorithm is going to work by first eliminating the quantifiers from the sentence to find a quantifier-free sentence, and then inspecting that sentence to see if that sentence is valid. So actually, I'm going to, having done this little bit of work here, I'm going to borrow that, and I'm going to build on that example in a new one. So the sentence is going to be for all x, for all y. If y is not equal to x, then there exists a z such that z is not equal to x and z is not equal to y. So if you want to, again, if you've got your one background process running in your brain and you've got some other spare cycles to think about something else, then you can try to think for yourself what a quantifier-free sentence equivalent to this would be. Well, I'm going to work it out methodically in the meantime, but if you want to just sort of try to see the solution, then you're welcome to do that. So I want to eliminate quantifiers from this using the algorithm we've got, which is basically the proof of the theorem that we had before, which the first thing to do is to replace the universal quantifiers with existential quantifiers. So for all x, for all y is the same as not. There exists x, there exists y, not y is not. So I'm basically going to sort of rewrite this sentence line by line, always having equivalent sentences. So y is not equal to x implies, well, we've just replaced the quantifiers here, so we'll keep this the same. Exists z, z is not equal to x, and z is not equal to y. Okay, so I've eliminated the, so I've written it in terms of universal of that. So let me underline kind of what we're working on. I've got rid of the universal quantifiers. We now want to eliminate the existential quantifiers from the inside out. So the inside existential quantifier is this one, that has a quantifier-free formula inside. Unfortunately, it's easy to eliminate that now because that's what we already did here. So we can replace that with this formula. So we get not exists x exists y, not y is not equal to x implies, and now we have either C, the cardinality is greater than equal to 3, or x equals y, and the cardinality is greater than equal to 2. And I've got one more bracket to close. Okay, so now we've got an existential quantifier here. We've got something inside. And to apply the process we had for eliminating an existential quantifier, we need to put the inside thing in disjunctive normal form. It's not immediate to see what that is, so let's do it in a couple of steps. So we've got not exists x, not y. This is the negation of an implication. So the negation of an implication is this and the negation of that. So this is y is not equal to x, and the negation here of this disjunction. So the negation of a disjunction is the conjunct, hang on. The negation of this is this. I hope I got it right here. Yeah, okay. No, it's fine. Okay, let's put it in brackets. So the negation of this is the conjunction of the negations of the two things. So we've got not c is greater than equal to 3, and the negation of this, which is x is not equal to y, or c, or not c is greater than equal to 2. Okay, it's hard to do things in one's head sometimes. Phew, that does seem to be what I've got written down. Okay, so we've now got these are conjunctions here, and we've got a disjunction inside. So we can distribute these conjunctions over this disjunction because we want to get the or on the outside to put it in negation normal form. Sorry, not negation normal form, in disjunctive normal form. So we have not exists x, exists y. So the first, so we've got the disjunction of the three conjuncts here. Y is not equal to x. It's not true that c is greater than equal to 3, and x is not equal to y, which is the same thing as y is not equal to x. So let's put that. So we've got y is not equal to x and not c is greater than equal to 3. We don't need to put y is not equal to x twice. Or from this disjunction, and we're distributing over the conjuncts here. So or y is not equal to x and not c is greater than equal to 3, and not c is greater than equal to 2. But this says the cardinality is strictly less than 3, and this says the cardinality is strictly less than 2. So the cardinality is less than 3 and less than 2 is just the same as saying it's less than 2. So we can get rid of this one. And we've got the disjunction of y is not equal to x, and the cardinality is strictly greater than, is strictly less than 3, and y is not equal to x, and the cardinality is strictly less than 2. This is a disjunction now, and because c is greater than equal to 2, sorry, the cardinality is strictly less than 2 implies the cardinality is strictly less than 3, and this is the disjunction. This is the weaker one. So actually this, well, anyway, we can just have this one, and we don't need this one. You can think about it yourself. If I start saying exactly why, I'll probably say it wrongly. So this is the same as there exists X, exists Y, such that Y is not equal to X, and cardinality is greater than equal. Sorry, it's not true that the cardinality is greater than equal to 3. That is, the cardinality is strictly less than 2. Okay, now we're finally in the form star here. So we've got exists of a conjunction of literals. Oh, but we're not quite in the form star because this one doesn't contain X. So we'll put it in star, so that's not exists X. So exists Y, Y is not equal to X. And not true that the cardinality is greater than equal to 3. Right. So this is now in the form star, and this says, of course, the cardinality is greater than equal to 2. So we can replace that by simply putting C greater than equal to 2, and it's not true that cardinality is greater than equal to 3. So now we've got another existential quantifier to eliminate, but there's no occurrence of X in here. We've just got a sentence, so we can just throw that one away. Okay, so this is just the negation of C is greater than equal to 2, cardinality is greater than equal to 2, and not true that the cardinality is greater than equal to 3. In other words, it's not, the cardinality is not greater than equal to 2, or the cardinality is greater than equal to 3. In other words, the cardinality is different from what? From 1. Okay. So I hope you can agree, it's not a totally trivial process. So there is some, what one's expressed, going from a first order formula to what's being expressed, takes a bit of work, and at the end of the day, we can have an algorithm that finds this quantifier-free sentence, and then we can inspect it actually in an automatic way here, and we can see that this quantifier-free sentence is not valid. It's obvious for us looking at it. Actually, there's an algorithm which will do that, which we'll see at the end of the lecture. It's obvious for us that this is not valid because this is not true. Sorry, this should say true too here.
Just a question. Can we further distribute out the existential quantifier into the first term or formula, and then because C3 doesn't include X, and then we get C is greater than or equal to 2.
Sorry, where are we talking?
From the first line to the second line, I'm pleased
on this,
how do we
here.
get C is greater or equal to 2?
Well, this is exactly the.
It's not because
right.
Yeah, we should prove this
right.
I think because C3 doesn't depend on X, so we can actually just switch.
Right. So how we get this is the process how we eliminate star from this theory FCB, which is again the answer to this puzzle question in the case that K equals 1.
Yeah, but I think it's easier because we can just.
So we're going to give a general answer to this question here for any K, and in the case K equals 1, so this says there exists an X, X is different from Y. That is, no matter what Y is, that is always equivalent to the statement that the cardinality is greater than or equal to 2. That is a quantifier free. That formula that has a free variable Y is equivalent to the sentence that the cardinality is greater than or equal to 2. Okay, and that will actually. So yes, I didn't. Sorry, when I said this is just the sentence cardinality is greater than or equal to 2, that was wrong. But this is we get this by applying the general procedure we have for eliminating, which I haven't shown you yet, that's your puzzle for the break, by applying this in the case K equals 1. Anyway, good question, and thank you for asking about that. So actually this says the cardinality is different from 2, so it's not valid because it is not true in structures that have 2 elements. Right, so okay, it's 1 minute past, so the break is until 16 minutes past 10. That's fine. Right, so this is the 3rd hour. Hopefully I'm going to be not as long as, so I'm going to hopefully finish a little bit before 11 today. The main thing left to do is to prove the 2 theorems we have. So theorem A, the decidability theorem, and theorem B, the elimination of quantifiers in the theory of finite cardinal bounds. So we'll start with theorem B, and then we'll use theorem B in order to prove theorem A. So let's prove theorem B. Proof of theorem B. And just to remind you, theorem B was the quantifier eliminability. So QE is an abbreviation for quantifier eliminability for FCB. Okay. So by our proposition, or lemma, but I called it a proposition, we just need to eliminate quantifiers of formulas in the form star. So we need to eliminate quantifiers on formulas of the form, I won't bother to write that, exists X, whoops, and then a conjunction of literals, each of which, so K literals, where each literal mentions each literal Li mentions X, contains X. Don't really want to think of literals speaking, but contains X. So our literals that contain X are very simple because they can't contain the propositional constants. They don't have any variables. So we've only got equalities and the negations of equalities as our literals. And to contain X, it means there are four possible forms of literals, as above, containing X. Namely, we might have X equals X. We might have X not equals X. We might have X equals Y. We might have X not equals to Y, where Y is different from X. From X, Y different from, sorry, my writing is not good. Y different from X. The first two we don't need to consider because, I mean, X equals X is simply equivalent to true, and X is not equal to X is equivalent to false. So we can replace those with true and false and pull them out of the existential quantifier. So we only need to consider literals X equals Y and X not equal to Y for variables Y different from X. But we might have several different such literals with different variables, as in this pattern here that I gave you as the puzzle to think about. So there are now going to be two cases. The first one is easy, and the second one is the tricky one. The second one is this one. So in fact, the first one is so easy, I'm going to squeeze it in at the bottom of the board. So two cases. or in fact, let's just write case one. Telling you there are two cases, but case one. One literal is of the form x equals y for some y. Let's just assume it's L1. L1 without loss of generality. It's L1 is x equals y. So now there's an absolutely easy quantifier-free conjunction of literals that's equivalent to this existential statement. Can anyone see it? That involves the same, well, at most the same three variables as. You simply, very good. So you simply replace, so if this is going to be true for an x equal to y, then it must be true if we replace x with y everywhere. And if we replace x with y everywhere, then we don't have the existential quantifier anymore. So we simply replace a quantifier-free formula, an equivalent free formula is L2, so LK, the conjunction of those with y substituted for x. And then we've got rid of the x, we've got to quantify a free formula in the other variables. So case two. So as I say, this is L1 without loss of generality. If we have any equality, we can always reorder them so it's L1, and we can do this. So case two is in which this is a conjunction of negations of equalities, of negated equalities, all of the form x is not equal to some different variable y. In other words, case two is exactly this. Okay, so case two is that we have exists x is different from y1 and x is different from yk. Now this isn't an exercise class, so I need to move the camera. So this isn't an exercise class, so I'm not going to ask somebody to come and solve it, but just out of interest, did anyone find a solution to the puzzle? Yeah. Okay, so sort of nodding, so maybe yes, maybe no kind of answers. So what I'm interested in, if anyone did find a solution and you have a better solution than the one I'm going to present, then please come to me at the end of the lecture and I'd be happy to discuss. Because mine is a rather complicated formula in terms of it's an enormous formula in size. So we want to replace this with an equivalent quantifier-free formula. So what we're going to do to understand what the equivalent formula is, we're going to think about when this is true in any particular structure. So in any particular structure, let's think about what y1 and yk are, y1, y2, y3, and we might have sort of y1 and y3 and so something and y7, why not? Maybe these all are all the same element in the structure. But maybe y2 is something different, as is y4, but y4 is the same as y, so maybe these are all equal. Maybe y2 is the same as y4, and maybe y6 and y5 are all distinct from everything else. We got 1, 2, 3, 4, 5, 6, 7. So, yeah. So in this case, we've got these 7 variables y, but these 7 variables y are standing for 4 different things. And so in that in a structure in which we have this configuration of equalities between the variables, this will be true if the structure has Well, in this case, 5 elements. In that case, we can find an x different from all of these. What's going on here? Well, the way we identify the variables in the structure amounts to a partition of the set of variables. Okay, so we want to think about what happens for any partition of the set of variables. Can somebody tell me what the Slovene for partition is? Partitia. Okay, that's good. So people know hopefully what the partition is. I'll just remind you. So recall a partition. A partition on the set. Partition on the set 1 to k is a set of a family of subsets of 1 to k that covers the set 1 to k and such that every set in the subset is disjoint from each other. So it's a collection of disjoint subsets whose union is the set 1 to k. So is a set P of subsets of 1 to k such that firstly the union of all these subsets is the set 1 to k, and secondly every I equals, so every element, so any 2 sets here are disjoint, or another way of saying this is that every element from 1 to k is contained in exactly 1 set in the partition. So it's contained in exactly 1 set in the partition. And let's write, we write curly P sub k for the set of all partitions of set 1 to k. So partitions are hugely studied in combinatorics, and it's a long time since I thought about anything like this or reminded myself officially, but kind of what I vaguely remember is that in the early part of the 20th century, one of Ramanujan's great achievements in mathematics was finding a formula for the number of partitions, but I might be wrong about that. Anyway, here's in discrete mathematics, there is the number of partitions is a sort of interesting number, and it grows quite quickly. So the number of partitions associated with a k element set gets quite huge. Right, so our equivalent formula, I've rubbed off the picture now, but the point is for whenever you have, well, whatever situation you're in, the identities amongst that holds between the variables y1 to yk will amount to a partition of the set 1 to k, and there will be some such identities that hold, so we can consider a disjunction over all possible partitions, and for any partition we want to say, well, the cardinality needs to be at least the number of elements in the partition plus 1. In which case we're guaranteed to find another element x. So our equivalent formula, our equivalent quantifier free formula, what that space is doing is going to consider a disjunction over every, so P ranges over an individual partition. So for every partition in PK, we're going to say, what we want to say is the cardinality of the structure is at least the number of equivalence classes in the partition plus one. So P is just a set of sets, so the number of equivalence classes is cardinality of P. So we want the cardinality of the structure to be cardinality of the partition plus one. And we want to say that the identities amongst the variables, we're really talking about the right case, so the identities amongst the variables are indeed those that hold in the partition. So for that, we say for every equivalence class X in the partition, and for every, so these are all finite conjunctions, for every I and J that are distinct in the equivalence class. Let me just, I've got a more complicated way of writing. I mean, I've got a conjunction over I and a conjunction over J. Let's just say for a conjunction over pairs IJ in X, when I is not equal to J, we want to say that Yi equals Yj. This makes sure that the equalities amongst variables are as in the partition. You could add also the conjunction saying that between different equivalence classes, you don't have the equalities amongst the variables, but you don't need to do that because if we have more identities than we're specifying, it means there are fewer elements. And so if the cardinality is greater than P plus one, if the cardinality stays as large, we still have room, we're still guaranteed to have the extra X we need. So that's why we don't need to put any negations of equalities in here, that you can do without losing the meaning. Anyway, that's it. So it's a rather huge formula because we have a disjunction over partitions, and then, well, once we've got an individual partition, this formula is not too big, but that's a very large disjunction line. Anyway, so we're done. So I hope you agree with me that in the end, it's maybe a little bit more combinatorially interesting than you might think at first when you first meet the problem. Right, so that's theorem B. So quantifiers are eliminable in the theory of finite cardinal bounds. So let's just now quite quickly prove theorem A, which is the decidability. Switch to blue. So proof of theorem A, the main result we had at the start, that the theory of valid sentences over the empty signature is decidable. So proof of decidability. So let A be a sentence over the empty signature. We need an algorithm that's going to return true if A is a valid sentence and false if it's not a valid sentence. So the first thing we're going to do is apply our implicit algorithm that we've got that will eliminate quantifiers from A in the theory FCB. So use the implicit algorithm in the proof of theorem B to eliminate quantifiers from A. Well, let's just say to find a sentence B in the signature of the theory FCB of finite cardinal bounds with these propositional constants for cardinalities in, with in the theory of finite cardinal bounds, B is equivalent to L. And we can do that because, as I said, quantifier elimination is an algorithmic process, albeit a very inefficient one, as long as we have an explicit algorithm for eliminating quantifiers from formulas of the form star, which is this form. And this proof that I did of theorem B, we started off with the formula of the form star, and there was nothing non-algorithmic in it. We got rid of equalities and non-equalities between the same variable. We then checked to see if there was an equality, in which case we replaced it with some simple substitution. And if everything was a non-equality, was a negation of an equality, then we did something complicated, and we came up with an enormously huge formula. But nonetheless, it's a formula that that one can write a computer program that will produce this formula, albeit it's going to take a lot of output space to actually print the formula out. But given that we're combining this enormous formula also with conversion to disjunctive normal form, where every time we get to an existential quantifier, it's really a quite computationally horrific process, but nonetheless, there is an algorithm there that's doing it. So we can algorithmically find this B. So what do we do with this B? We want to decide if it's valid. So for validity, it's useful to convert formulas to conjunctive normal form rather than disjunctive normal form, because formulas in conjunctive normal form, it's a conjunction of things, and a conjunction of things is valid if and only if each of the conjuncts is valid. So if we convert B, so let me stick to the notation of my notes. Find a formula, an FCB formula, an FCB sentence in conjunctive normal form, from CNF equivalent to B. So when I say find one, we do the algorithm. Now, yet another inefficient algorithm, again, for converting to conjunctive normal form. So conjunctive normal form is a conjunction. So here I'm using M. For each DI is a disjunction. This is a conjunction of disjunctions of literals. So each DI is a disjunction of literals. Disjunction of literals. So because this is a conjunction, it is valid, as I said, if and only if each DI is valid. Then so A is valid. The original A is valid if and only if B is valid. B is equivalent to this, and this is valid if and only if each DI is valid. So A is valid if and only if every DI is valid. With each DI is of the form, well, it's a disjunction of literals. So disjunction of literals, well, our only literals here are propositional constants or their negations. And our propositional constants are these C greater than cardinality greater than equal to M propositional constants. So it's of the form C some disjunction of positive literals. So this might be C is greater, cardinality is greater than equal to N1, or the cardinality is greater than equal to NK. Or it's not true that the cardinality is greater than equal to M1, or it's not true that the cardinality is greater than or equal to mk prime. Right, so some disjunction of positive literals and disjunction of negative literals. So the cardinality is greater than or equal to this, or the cardinality is greater than or equal to that. These positive ones are the same as saying the cardinality is greater than or equal to the minimum of those numbers, okay? The disjunction, the cardinality is greater than or equal to 2, or the cardinality is greater than or equal to 3, is the same thing as saying the cardinality is greater than or equal to 2. Right? And the negation is the same as saying it's not true that the cardinality is greater than or equal to the maximum of those M1s. So this is valid in FCB if and only if you can think about it in your own time. The minimum of the N1 through to Nk is less than or equal to the maximum of the M's of these bounds of the M1 through to Mk prime. So if this is true for every DI, we return yes, and if it's false for one DI, we return no. So if, let's call this star star because we had a star earlier. So if star star is true for every DI, we return yes. Otherwise, return, by we, I mean our algorithm, we return no. So yes, it's valid, no, it's not valid. And we're done. We've proved theorem A, well, we've proved theorem B, now we've proved theorem A. So just want to end with one further remark, which is, so this is one application of quantifier elimination to establish decidability, and it's an important application. So this is something that it's actually used for in practice, in some sense. It's relevant to stuff that people actually do in computer algebra. I may talk a bit more about that next week. But I do want to just say one can get additional information about quantifier elimination. Sorry, additional information from quantifier elimination. So there's an exercise. There's an exercise. Get the following information out of quantifier elimination. So by using quantifier elimination in combination with, so in the proof of decidability, we put things in disjunctive normal form, so in conjunctive normal form. It's also, you get a lot of information from quantifier elimination by putting the sentence also in disjunctive normal form. So by using quantifier elimination in combination with disjunctive normal form, prove that every sentence over the empty signature expresses one of the two properties. Expresses one of the two properties below, or the two kinds of properties below. So a sentence can either say cardinality of the structure M belongs to F, where F is a finite subset of natural numbers. So we can either say the cardinality belongs to a finite set, or the cardinality of M does not belong to F. So the only things we can express are the cardinality belongs to some specified finite set, or the cardinality does not belong to some specified finite set. So when I was thinking about how to write this, I was going to say the only things you can express are the cardinality of M belongs to F, or the cardinality of M belongs to, for a finite set, or the cardinality of M belongs to F for a cofinite set whose complement is finite. But then I realized that was wrong. Can anyone see why this is different from saying the cardinality of the structure belongs to a cofinite? The second statement is different from saying the cardinality of the structure belongs to a cofinite set of natural numbers. It doesn't say that. Because the structure can be infinite. So the point is, in the second case, in the first case, the structure cannot be finite, cannot be infinite. In the second case, you're always allowing an infinite structure. And those are the only two possibilities. Okay, so that's everything for today. Next week, we're going to see a more mathematical application of, so this was quite a logical application of quantifier elimination, which is appropriate for a logic course. And next week, we'll see a more mathematical application. Okay, I'll stop the recording.